Okay, gravitational field measurements. Welcome to the Heimdall project. So I'm going to talk about gravitational field measurements, which is a paper that I wrote, which presents the pan-gravity method. It's an energy-based technique for measuring gravitational field strengths without mass, only using radius, orbital velocity, and rotational velocity. Um, that's pretty much it. It's very quick, very easy, and I want to jump right in. Okay, gravitational field measurements. Welcome to the Heimdall project. So I'm going to talk about gravitational field measurements, which is a paper that I wrote. So this is the gravitational acceleration equation from my gravitational field measurements paper. Basically says um, gravity is the gravitational constant times the energy density of the gravitational field, not the planet or celestial body, gravitational field, times the system's volume times the speed of light over the radius squared, or times the speed of light squared over the radius squared. Um, so gravitational acceleration relates to energy density, space-time geometry. So that's the big thing here. Energy density of the gravitational field and space-time geometry. So that energy density comes from the shape of the field and the movement of the field. So you'll see that as we continue on. This formulation ensures that gravitational acceleration emerges as a function of energy density and field geometry, rather than mass as the fundamental input. So depending on energy density, this highlights how gravitational interactions emerge or arise from energy redistributions, reinforcing the energy only framework. I'm you can think of this as a practical extension of Verlindy's emergent gravity. So, and I have more papers on this, which I actually developed separately before reading through his work, but I realized that we had hit on the same thing, which is fascinating. Um, but the when I'm saying gravitational interactions arise from energy redistributions, we're talking about entropy here. There's an organizing influence reinforcing this energy framework. So these aren't this isn't a mathematical trick. Everything is tied to the stress energy tensor. But as you get into it, you realize there's a logic to how everything works. It's entropy and information. So we had almost everything we needed um, to calculate gravitational field strength from that first equation. The only thing we didn't know was energy density. So the entire pan-gravity method, nearly the entire pan-gravity method, is focused on finding the energy density, UG. Um, so we have this equation. So the energy density of the gravitational field um, is calculated by multiplying space-time elasticity, the elastic, which represents the energy contribution from space-time, right? Space-time elasticity. The surface area of the system, and then the correction factors, surface to volume scaling corrections, and the localized energy transport anisotropy. So this equation, ensures that energy density is accounting for geometric stress components of the gravitational system without inducing mass. So we're capturing it from surface area, so the area around a celestial body, right? And that is the interaction of space-time and the celestial body. So very important. Beta and gamma are surface to volume corrections and energy transport anisotropy. So basically, what is happening with energy density, as you'll see as we get into the elasticity calculation, is we're basically finding the potential energy in the reaction of space-time to that celestial body. So how much energy is space-time putting into its reaction to this celestial body moving through space? Does that make sense? Okay, so to find that energy density, here's where we get into it. Like I said, we need space-time elasticity. So our space-time elasticity equation quantifies the elastic response of space-time due to rotational energy flux, serving as the foundation for gravitational modeling. So by incorporating rotational effects, provides a direct measure of how energy redistributions influences space-time curvature in systems dominated by rotational dynamics. So like I said, this is important because the V orb and T rot, so that's orbital and rotational speeds, right? Those are going into this calculation. So the rotational and orbital speeds, the area and the volume, radius, and the stress energy correction factor are accounting for how much this celestial body is moving and how stretchy space-time is, because how stretched out is space-time responding to the movement of this celestial body. It's not just a static body in space. So if it were, we would remove the orbital and rotational inputs, and we'd get a widely different answer that would not give us the correct results. So for anybody that has wondered, does the rotation and orbital speeds of a celestial body matter to gravity? Well, in an energy-based approach, it's extremely important, because we're stretching space-time. So this elasticity is important because if you think of the planet or a moon or whatever, or a star as an inclusion in space-time, and if you think of space-time as an ocean, which is how I think of it, which is actually what helped me develop this method, then you don't just have something sitting in this space-time ocean. You have something sitting and moving in the space-time ocean, creating this inclusion and creating a response from space-time. It's not just sitting in a static thing. Space-time is responding to it and moving around it. Okay. So by incorporating these rotational effects, it provides a direct measure of how energy redistributions Entropy, once again, influences space-time curvature in systems dominated by rotational dynamics. So let's move on. So we already know our orbital and rotational velocities. We can already find area and volume, radius. But now we need to use area and volume to calculate this stress energy correction factor. Why is this important? This is one of the things that helps us that helps this method to adapt to any system size. So this could be Halley's Comet, or a very large star. You could also use the same method to do basic measurements around a galaxy. The scale doesn't matter, as long as you use this and you think cleverly about it. For a galaxy, it would be a bit more difficult because there are some things that would take a long time to measure, and might be a little uncertain. But so maybe don't use it for a galaxy unless you need to. I have another method for that. But the delta stress energy correction factor is important. So introduces an area volume dependence. So our entire calculation relies not on the mass, but on the surface area and volume of the system interacting with spacetime, ensuring that these geometric constraints are properly incorporated into the elastic response. So what does that mean? It means that the geometry, not the mass of the system, is extremely important. So these properties define how spatial stress energy terms scale with system size, reinforcing the dependence of elasticity on geometric factors. So I'm going to say it. I just said it. The geometry of the system matters, not the mass. If you really just rip everything down to the bare bones, mass is energy, right? This is an accurate way to measure the energy happening within this geometry. So I just want to emphasize that I'm not saying the mass-based method, the mass-centric method, is wrong, but it's highly dependent upon estimations. What I've developed is a way to take guesswork out of it and capture the energy interactions that are happening, which is what we're doing with mass, by the way. Mass is just energy, but we're guessing how much mass is there. This, number, we don't know how dense the planet is or whatever, right? There's a lot of guesswork in there. We're looking at how it's pulling on other things, unintentionally measuring and, taking a partial energy-centric approach to a mass-based method. So I've basically taken the mass guesswork out of it and said, okay, that's a lot of work. Let's find a way to do this with just geometry and movement. Yeah? Okay. So we'll walk through that later. Okay, so this is the modified Einstein field equation that I just wanted to share so you guys can see what's kind of happening under the hood. This is how I'm achieving what I'm achieving with my method. You don't have to do any tensor calculus. So this is what my equation is. My gravitational field measurements equation is taken from this and done in a practical way. So instead of doing tensor calculus, I'm like, how can we just cut to the chase here, make it simple and accessible? Somebody had to do the work, so I did. The inclusion of these two terms account for spatial stress and isotropic stress gradients. And they both modify how energy propagates through gravitational field, once again influencing energy redistribution of energy in response to space-time curvature. This basically says what Eric Verlinde says. It's all about entropy, baby. And these additional terms, which are just saying we need to capture other stress components other than just mass. Okay, so it makes it not mass dependent, and you have mass energy terms as well. Okay, that is the simple way to say this. I don't want to go crazy there because that's in my paper and you can read my paper. So those extra terms in the modified Einstein field equation, which everybody was like probably thinking, I don't want to calculate that. Well, you don't have to. I developed this. So I have alpha and beta correction factors. Once again, you can read, you can read about why these correction factors exactly in more detail in my paper. So the correction factors beta and gamma serve as geometric scaling mechanisms to account for deviations of perfect spherical symmetry in real celestial bodies. In other words, it's saying, hey, in real life, things aren't perfect, which is partially what's happening in the modified Einstein field equation, is saying, okay, in the mass space approach, you have this thing perfectly sitting on the rubber sheet, right? Per the normal analogy, but it's 4D spacetime. You don't see that, right? So you have this thing sitting on the rubber sheet, and theoretically, it's perfectly symmetrical and spherical. That it's not accounting for imperfection. It's not accounting for a banana-shaped moon, which we don't have, but maybe there is. You never know. If you had a banana-shaped moon or banana-shaped sun, it's not going to account for that. So these correction factors do account for that. So if you're like, this is my radius, but also if you say this, you have a radius and you found a way to calculate the surface area of a banana, that banana-shaped celestial body. Excuse me, sorry. And the volume, then you're going to need these correction factors to account for the imperfections, right? But if you just took the banana and you said, this is what I think the mass of it is, it's not accounting for actually how space-time is responding to that specific shape. So alpha and beta correction factors are saying, okay, there are stresses on celestial bodies, and they come in all different shapes and sizes. And this is the way that beta and gamma use the additional terms in the Einstein field equation to account for that. So these factors ensure that energy density calculations remain accurate regardless of an object's shape or mass distribution, effectively modifying the gravitational field response based on how energy is redistributed in spacetime. Once again, focusing on the nuances of how entropy is happening here. So the correction factors beta and gamma emerge naturally as scaling terms that correct the way energy flows through a gravitational field. So their role is to adjust the Einstein field equations, which I was just talking about, to reflect this non-linear behavior of stress energy space-time. And you'll see those in actions. Like, it's not just there as a correction. It's not a scaling. I mean, it is a scaling mechanism, but in an energy-based approach, when you're relying on geometry, if you have a planet that has a large chunk out the side and you're using a geometric approach and you've captured the radius, I mean, I said this before, you're going to have an inaccurate read of the amount of energy that's actually moving through space-time. Okay, so now we have nearly everything we need to find the energy density, complete our energy density calculation of the gravitational field, which we needed surface area, space-time elasticity, and gamma and beta. And once we get the energy density for the gravitational field, we'll be able to measure, or to finish our calculation, or just do the calculation for the gravitational field strength of Venus, which is what we're tackling here. So we have all of the information that we've gathered so far. The observable parameters: radius, orbital velocity, rotational velocity. We've calculated surface area, the volume of the system. Here, and I've just done this ahead of time, but I've shown my math here. And then I did the space-time elasticity calculation. I did which included doing a calculation for delta. And I calculated the beta and gamma correction factors. So now we have all the inputs for energy density. I do want to say one thing though. Okay, so you have three observable parameters: radius, orbital velocity, and the rotation. Radius in meters, orbital velocity in meters per second, rotational period in seconds. Getting those right is important. So when you're writing down your observables, make sure it's in radius in meters, orbital velocity in meters per second, and rotational period in seconds. Screwing those up, I mean, obviously, you guys know, messing those up is going to cause you problems and you won't know where you went wrong. But it's luckily an easy enough calculation that you could just start over. Listen to my video, me scolding you, using the right, using everything correctly. Okay. So if there's a situation, you're at work, you are like, okay, I'm going to try out Chris's method, this pan-gravity method. It won't take very long, but I want to test it out to see if he's full of crap or not. And so you find an exoplanet that you're working on. I'm assuming everybody watching does exoplanet research. I'm just kidding. The millions of you out there doing exoplanet research. So you figured out the radius of this planet you're looking at, or whatever. You figured out how fast it's orbiting its star. But what you don't know now, you're like, oh, I don't know this rotational period, but he has rotation on here. So what I have found, Venus has an extremely long rotation. What I have found is you can use a 15-hour rotation as a placeholder to get your, and you'll still get a correct answer. The reason why I use the exact rotational period, because I really like to be extremely exact. But and it's good to be, when you know the rotation, you should use the actual rotational period. But you can use a 15-hour rotational period. That's 54,000 seconds. 54,000 seconds, 54,000 seconds. So use that as a placeholder. For instance, the rotational period of Venus, 20 million seconds. Okay. 21 million seconds approximately, right? And you'll see at the end of this, we're going to get the correct uh, gravitational field strength, which is 8.87 meters per second. So you're going to get the actual gravitational acceleration, right? However, substituting that 54,000 second is going to give you the same answer. And your variance is only going to be off at 10 decimal places. So does the rotational period matter? Yes. Is there a reason why I said 15 hours? Yes. You can't do a zero. You can't pick a rotation that's too slow for smaller planets. So 15 hours is at this point ideal. And that is testing that on the slowest and fastest rotating bodies in our solar system. So Jupiter and Venus. I did a bunch of calculations, and they're all really close. And I like everything to be really exact. So using those as a case study, it worked out really well. So even if it's off from what the actual gravitational acceleration ends up being for a planet, when we actually visit it and are able to measure it, it's not going to be off very much. It, 8, 9, or 10 decimal places, which nobody really cares about. So that's all I have to say about that. So let's move on and finish our energy density calculation. Okay, so on this last slide here, measuring the gravity on Venus, we took our inputs, space-time elasticity, the surface area of the system. That's surface area off of radius. So in order to get the true surface area, we have beta and gamma correction factors to account for variance. And we are able to calculate the energy density of the gravitational field. And I'm going to say one more time that this is not the energy density of the celestial body, the object in space. It's not the energy density of the object in space. For those of you that are thinking that this is many orders of magnitude smaller than the energy density of Venus, you are correct. This is measuring the energy density of the gravitational field. So there. Okay, so gravitational acceleration. We're back at that first equation that I shared, which is my equation in the pan-gravity method. I can't believe I spelled gravitational wrong. For gravitational acceleration. So G, gravity, equals the gravitational constant, that extremely small number, times energy density, which we spent that entire calculation getting 7.24581 times 10 to the negative 3 joules per meters cubed. Finally got that number. And then we're going to multiply that by the volume of the system and the speed of light squared over the radius squared. And as you can see, I believe, so I went to 8 decimal places, right? I believe this is highly accurate. And I went to 8 decimal places because I wanted to see, is it picking up anything else? I published it in my paper. So one day when our tools are super sensitive, we can see I'm correct. You go stand on Venus, guys. Don't get burned up. Go measure the gravity for me. Um, okay, so the gravitational acceleration. So now that we have done the energy density calculation, and we have gravitational constant times energy density. So times energy density times volume times the speed of light squared. So now we can really think about what is happening in this equation. So we went through the energy density calculation, which is calculates the elastic energy potential of the interacting space-time with the geometry of the celestial body. Okay. So when we have the energy density term in there, this is what it's saying to me. So my equation says that the elastic response of space-time presses in on the geometry of the celestial body, creating gravity. It's a reaction. So this actually says that gravity, this organizing of energy and energy redistribution, energy and information redistributions, is a sort of pressing in on the geometry of a celestial body or an object in space. Very similar to an object in an ocean, which is why I say space time is an ocean. It's a space time ocean. It's the only way to really think about it, in my opinion, and have things start making sense conceptually. So when you stop thinking about space time as a static medium, you're dropping a ball, things are moving around another ball with another ball, and two balls are next to each other, and they're attracted to each other. Okay, subtle joke. Um, this is saying that no, it's not like that. We're in a 4D space-time ocean where objects in space are causing energy and information redistributions, and space-time is responding to that. Okay. This is the physical side for simply for demonstrating measuring gravitational field strengths on celestial objects. But this is the physical side of that entropy, emergent gravity. So gravity is emerging from this interaction because it becomes the pressure of space-time pressing into the center volume of a celestial object. You see, it's another interpretation that actually works um, without guesswork. So I'm not guessing what the mass is. Not saying, well, I think this I think the celestial body is probably made of this and that, and I don't know how dense it is, but maybe the mass is somewhere around this, judging by what I know of other objects in space. I'm saying, well, I know the geometry. I know how fast it's moving and rotating through its solar system or wherever it is. That's enough information for me to calculate the gravitational field strength, as among other things. Um, on the other side of this, so like I think I said this before, but we're not actually calculating anything about the celestial object itself. Everything is about the geometry of space-time. So space-time is curved around an object, right? And the volume and surface area that we're calculating is the displacement of space-time. Okay, we're not calculating the mass or size of an object. I know it seems like we are, but all of that goes into calculating space-time. Space-time's energy, space-time's elastic response to objects moving through it. I hope you guys enjoyed this. Please try the method out. It's super simple. As you can see, it's a really simple equation based on Einstein's field equation, but really pulling in the other stress energy terms. Yeah, this was kind of a fun project for me. Leave some comments. Please try it out. If you have questions or if you're running into issues as you're getting into doing these calculations and thinking about the theory behind it, if you have questions, leave it in the comments. But I'm very curious to see what other people think. Check out my paper. I'm going to leave the link. And thank you so much for watching.